Great. Good morning, everyone. Thanks, Catherine, for the very nice introduction of the PRS in very high level. That makes my talk much easier to do. So I'm Hailiang. I work at MGH, Mass General Hospital and the Broad Institute. And it's my pleasure here today to walk you through how to calculate the polygenic risk score. So I'll give a lecture roughly for an hour. And the computation associate, in my lab, Alice, will walk you through how to actually do the calculation on the server. Hopefully it works better. So without further ado, let's get started. So how to calculate the polygenic risk score? So as you know, the polygenic risk score, or PRS, is a characterization of an individual's genetic risk to a disorder or a complex trait. So to put it in a very generic term, the polygenic risk score, or PRS, is a summation of your genetic profile times the risk of that genetic factor that confers to your health. So this is a very generic formula, but of course, in practice, things are always more complicated than what the formula tells you, and we can walk you through. So I'd like to recommend this very helpful, review paper written by Paul O'Reilly's team. So it's a tutorial in how to run a polygenic risk score analysis. There are several major steps, including first, to ascertain the data. You'll need at least two sets of data. One is called the base data, or the discovery data, which is basically the GWAS summary stat you can download freely from the PGC website. The next data set, the second data set, would be your target data set. That is a data set you want to predict the disease risk in. For example, your own cohort, you want to calculate the PRS for. Then you need to do QC. Of course, I'm sure you heard a lot of QC yesterday. I'm just going to walk you through very quickly, very soon. And then it's a final modeling of the PRS. I'm going to walk you through with details. After that, you would do some testing, either visualization or calculate the matrix to characterize how well the PRS makes a prediction. And finally, sometimes you want to do a validation to make sure it works. So now let's dive into all this one by one. So I'll skip the data set, assuming you will be able to download the summary stat as well as having access to your own cohort. So the next thing would be to do the QC. So the first step of the QC in calculating the PRS is to make sure the GWAS summary stat actually works. So you probably don't have to worry about those you downloaded from the PGC website, but in case someone handed over a summary stat to you, it's always good to do a sanity check. And one way to do that is to calculate the heritability in that GWAS summary stat, which I'm sure you heard about yesterday. You can run LD score regression on the GWAS summary stat so that take a look at how heritable the trait you are studying is. It has to be heritable to some extent so that it has genetic contribution to the disease or the trait. All right, the second part is a standard QC on the target data set, which is pretty same as what you learned yesterday. Just do regular QC, the genotyping rate, Hardy-Weinberger, equilibrium test, imputation information score, for example, sex check. So these are all the regular QC to make sure your target data set is clean and as free from genotyping error as possible. So the next is a little bit unique to the PRS analysis. That is the genome build. Genome has several builds. I started with build probably 35, and now we're at 37. So once every 5-ish years, you will have a different genome build. The good thing is the new build always covers more part of the genome, but the bad thing is the genome, the coordinates for the variants you're working on changes. Right? So if you have build 35 in the GWAS summary stat, but you have build 37 in your target data set, the two don't match. So you have to match the SNPs in the two data sets so that you can use the discovery or the base data to make the prediction. And luckily, there is a tool for you to do that. It's called Liftover. You can simply go to this website. You just upload a list of the SNPs in your summary or in your target data set, and the website will do the job of moving this from one build to the other so that the two data sets have the same build. So this is something unique to the PRS analysis. The next would be the remove the duplicated and non-resolvable mismatching SNPs between the two data sets. So that's also unique in that you have to get rid of all the SNPs that present in the base data but not in your target data, or vice versa. But this is not going to be a major issue because you won't be able to leverage any of these SNPs anyway. So this will be naturally done by most of the PRS calculation software. The next thing that is a little bit unique to the PRS and also confusing is strand flipping. So I'll give you one example, and I'm going to ask every one of you to answer the question, and we'll do a little bit exercise here. So let's say I hand over a data set to you, and you know for a certain SNP, there are two alleles in the data set. One is allele A, which is treated as baseline allele with baseline risk. The other allele is allele G, which has twice as much risk as allele A for the carrier. And assume this is multiplicative risk, meaning that if you have two Gs, you have two times 2 risk. All right. So this one is the first question is very simple. Assume your target data has an individual who is a GG carrier. How much risk this person carries? Raise your hand if you think it's 1 baseline. Raise your hand if you think it's 2. Raise your hand if you think it's 4. Yeah, right, good. All of you got it right. So what if you have a TC variant? How much risk the CC individual carries? 4, right? Anyone who don't agree is 4? All right, so this is pretty straightforward. Now, here's what is called ambiguous SNP. It's the same situation, but instead of an AG SNP, you have an AT SNP. So A allele is a baseline, T allele is twice of the risk. What is the risk for TT individual? Anyone tell me? Anyone has an answer for that? We don't know, because we don't know the strand, right? It could be on the same strand as the discovery data set. So if TT is 2 times 2 is 4 times of the risk. It could be the strand got flipped, but you have no way to tell because A, if you flip A, it's going to be T. If you flip T, that's A. So you get the same AT, and you have no idea what it is. So it is very important in the PRS calculation, you get rid of those ambiguous SNPs. Otherwise, it's going to just flip your scores around. If I remember correctly, there are roughly 15% of the SNPs that are strand ambiguous. So if you don't remove them, these are going to contribute noise or even bias your result on, towards one direction. That's a common mistake some people make. All right. So the next is the sample overlap and relatedness between discovery and the base data set. So it is very important that there is no overlap between the discovery and the target data set. Even if you have a huge discovery data set, let's say PGC has a 1 million sample study, and you have a 10,000 target data set, and maybe there are probably 1 or 10% or 20% of your data that might have been included in PGC for some reason. For example, they both belong to a certain biobank. And you probably tell yourself, okay, 10% of 10,000, that's 1,000. 1,000 out of a million, that's very small. But that's not right. The ratio that matters isn't the overlapping sample divided by the discovery sample size. It's the overlapping sample divided by your target sample size. That means if you have 10% of the data that's overlapping with the discovery, the 10% is the percentage that matters, and that's going to change your prediction quite a lot. Sometimes it's hard to remove the overlapping sample, and it's getting honestly more and more difficult. PGC is getting larger and larger, and it's very likely you share some of the biobanks. But this is the due diligence you have to do. Go to your data sources to make sure there is no overlap. And when there is a doubt, it's always a good idea to exclude the overlaps or even the relatedness. Even there could be a family member, one belongs to your study, the other belongs to the discovery study. And if there's any doubt, it's always a good idea to exclude the overlapping sample. If 10% is going to do make a very big difference in terms of the prediction. The prediction accuracy is going to give you a very false inflation of the accuracy that you were not expecting. All right. So, any question on the Q? Oh, yes.
Why should we exclude the related?
Because the related share part of the genome. Let's say if you have two individuals, or if you have one individual that's fully overlap, it's about equivalent as if you have two individuals, three individuals, they share part of the genome, like parents or child.
But isn't it what we want to capture?
In the training, probably not, because when you tune the model parameters, it's going to be sort of tailored towards the training data set. And when you have a testing data set that is related or overlapping, the discovery is going to be something called overfitting. You're basically using part of the knowledge you know in the training to make the prediction in the testing. Yeah, so, yes, go ahead.
Yeah. So, what about relatedness within the target data sets? Let's say we have siblings or first degree or second degree relatives.
Yes.
Within the target samples, do we need to just need one sample if they are two duplicate individuals, or softwares some softwares can do that?
Yes, so that's a good question. In the target data set, you don't have to remove them, but you probably won't be able to use what I'm teaching today to calculate the accuracy, because if there's a related structure, you have to capture them in characterizing the accuracy. So there could be a linear mixed model with a family structure built in for you to calculate the accuracy.
So we don't need to remove them, right?
You don't have to remove them. You can still use them. It's just when you evaluate the accuracy as R-square from the linear regression, that's probably not right. But there's a way, I believe, you can put the family structure in the model so you get a more accurate estimate. All right. Yes? Oh, we shouldn't. I guess most of the study we are not allowed to do the re-identification. So what we do is usually, try to avoid all the samples from that country. For example, if you do a prediction in Japan, you probably want to exclude all the Japanese cohort in the PGC. So PGC can do the leave one out summary set for you. You want to exclude all the Japanese cohort. This is not identify the individual, but try to identify the source of ascertainment. That's for one, one way you can do that. Or you can try to exclude all the sample from UK Biobank, no matter whether, the individual are included, but entire biobank will be left out. Yes?
Just a quick remark about sample overlap. I know that it's a great idea to go half-field independent training test, but could you adjust your training, the baseline prediction by permutation testing, so that it's not just, your chance is shifted. So if your baseline accuracy, 0 and 1 classification is no longer centered at 50%, but shifted by the amount of overlap.
Yeah, so I have to think more carefully on that, but I think even if you do permutation test, there could still be inflation. Yeah, so I have to think more carefully on that. So if you have overlapping sample, and if you do, but I guess even if you do the, I guess in terms of the prediction, prediction evaluation, you might be able to use the permutation to tell whether there's really power for the PRS to differentiate case versus control, for example. But the model won't be able to be transferred to other places, right? So it's possible to fix that by permutation, I think. Yeah. All right, any other question? All right, if not, let's get on to how to calculate the PRS. So the PRS, if you want to reduce it to a simpler, simpler problem, that's basically just two things you need to do. One is to choose the right SNP, and the other is to pick the right weight, which are, neither of them are trivial, but we're get through the steps for that. So again, I'm showing you the equation. PRS is simply a summation of the risk contributed by each of the SNP. The challenging part would be how to pick the right SNP and how to get the right estimate of the risk for each of the SNP. So which is summarized here, the choice of the variance and the adjustment of the effect size. So there are two things you need to be aware when you pick the SNP. One is you want to pick the causal SNP, not the non-causal SNP, which is, of course, clearly, I'm sure you know why, but it's challenging because you actually don't know which is the causal SNP, which is the non-causal SNP most of the time. And there are methods like phi mapping that can give you some of the clue, but unluckily, phi mapping requires a lot of statistical power. That means out of the 300 loci in the latest PGC schizophrenia paper, you probably will only be able to do good phi mapping in 20, 30 of them at most. For 90% of them, you don't have the power to do phi mapping to tell you which one is causal versus non-causal. So this is a challenge for the PRS approach. And the second one is the LD pattern. So LD pattern is, let me show it here. The SNPs are linked, because during the meiosis steps. And let's say you have two causal SNPs, one causal SNP here, and the other causal SNP here. The correct way to calculate the PRS is to calculate the contribution from this causal SNP and from this causal SNP, and you put them together. However, you don't know which of them are causal, as I told you. And if you do a naive way of PRS, you just add everything up. What's going to happen? You're going to overcounting the risk in this block, and you're going to relatively, undercounting the risk in this from this causal SNP. So being able to correctly model the linkage disequilibrium so that each of the individual risk variant has been counted independently is something very important in the PRS step. And I have to say this is a little bit different. Both of them are ways to capture the causal variant, but the first one is more referring to whether you can distinguish there's a causal signal or not, and the other one would be to, there's a causal signal, but which one is the best SNP to include. All right, the last step is to adjust the GWAS effect size. You probably saw, from the GWAS summary stat, you have the beta, you can just take it. However, that beta is usually not, theoretically it's not 100% correct because you need infinite sample size to get a absolutely correct beta. The beta will only get to the true estimate if you have an infinite sample size. Even with the ever-increasing sample size, for a lot of the betas, we don't have the fully correct value. And to make it worse, a lot of the study do a p-value cutoff. You only keep the top SNPs, let it be top 10%, top 20%, and that will cause a winner's curse. To put it in a simple way, the beta can be estimated to be larger or smaller than the real beta. And if you put a threshold there, it will always be the beta estimate that is larger than the real beta stay in your prediction, in your GWAS. If you get a smaller beta, it's less likely to be included. So if you have any kind of cutoff, you will have a winner's curse. You are overestimating beta over the whole genome. So how to reflect that? So that's the other thing we have to consider. So I'm going to introduce first the naive way of calculating PRS. It's important because it's still being used in many of the papers, but I don't think any of us would want to use it, as I'll introduce the Bayesian way, which is a much better way to do that. But I think it has all the concept and solutions to the problems we proposed. It's good to walk them through. So the naive way is called clumping and thresholding. Or C plus T. C means clumping and T plus thresholding. If you recall, I proposed 3 challenges in my last slide, being able to identify the causal variant, model the LD, the linkage disequilibrium, and also adjust for the effect size, right? 3 of them. So the 3 of them, two of the 3 of them are being solved in the T step, which is the thresholding step. The thresholding step simply set up a GWAS p-value threshold. Anything below that threshold will be, removed. Anything beyond that threshold will stay. All right, so this solves the causal problem, well, this attempts to solve the causal problem and the effect size estimate. Why? The underlying hypothesis is, if you have a very significant p-value, that means usually you have some causality signal there. So that's how it solves the, causality problem. And also, by discarding the SNP, below the certain threshold, that effectively assign their effect size to 0. That's kind of a shrinkage to give them no effect. So both of them are very naive, as you can tell. That's why it's called a naive approach. The C approach is called clumping. That is, it gets rid of all the SNPs in LD with the lead SNP, so that you can sort of remove the contribution from the nearby SNPs by the LD. So I'm going to show you one example. So thresholding and the clumping. So thresholding is simply setting up the threshold, getting rid of everything below that, because we don't believe they're causal. And clumping is you start from the best SNP, you find out which SNPs are in LD with the best one, and you get rid of all of them. So in this example, you're going to get rid of the SNPs at the bottom through the thresholding, the SNPs in the circle through the clumping, and you only keep this SNP in the PRS calculation. So any question in this naive approach and the 3 major challenges? Look good? Yes?
Is it really accurate to erase all the elite variance, like in the clumping?
No, that's not correct. So, I mean, this is a very coarse, very rough estimation, approximation. So I'm going to introduce the Bayesian method that works better. This is the early day method. Before all the Bayesian method, people do that a lot. And some people do that if the sample size is small, it probably doesn't make much difference. Or if the focus isn't getting the most accurate PRS score, people still use that. You will still see that in literature, but I don't recommend using this approach. But it's a good approach to show how things are being done in creating the PRS in a naive way. All right? So if you want to try this out, there's a package called PRICE, PRS-CSx. So you can go to the website and download the software that would basically do the naive approach for you, which is kind of a very straightforward. Like I mentioned, I don't personally recommend. Oops, you can take photos. Sure. Well, I'm going to share the slide deck. Yeah, don't worry. So, like I mentioned, I don't recommend using the naive approach. Usually, the Bayesian approach works better for all the reasons I have told you. So first, even you have a p-value threshold that is very liberal, 10 to the minus 3, there could still be the causal signal below that threshold. And the reason is we are working on a very polygenic disorder. Some of the SNPs have very tiny contribution that you don't have the sample size to capture. So usually it's a good idea to include all the SNPs in the model. And also, we mentioned Werner's curse, right? And by just getting rid of all the SNPs below the threshold wouldn't fix the Werner's curse. You need a more principled approach to fix the beta effect estimate. So the Bayesian approach is able to include all the SNPs in the model, and by all the SNPs, I mean usually 5 million SNPs, 7 million common SNPs in the GWAS summary stat, and they're able to include all of them in building the model. And how do they do that? They would assign a new beta to each of the SNP. That the new beta meaning you are not actually taking the beta from the GWAS summary stat. You take the beta, you do a Bayesian modeling, and that would give you an output of the new set of beta that solves the LD problem, solves the causal SNP problem, and solves the Werner's curse and the GWAS effect size adjustment problem. And that new beta is going to give you a much better estimate of the PRS. And how do they do that? They do that through the prior, which is shown here. And as a comparison, I told you the clumping and the thresholding to some flavor does that as well in a very naive way. And there are other approaches called frequentist approach, for example, lasso, ridge, or elastic regression. And they do that by putting a constraint on the beta. For example, they require beta to sum up to a very small number so that you can't inflate the beta all the time. But I'm going to skip this because most of the frequentist approach require individual level access to the training data set I mean, you typically don't have. You have the summary stat, but you won't have the individual level, access. So we're going to focus on the Bayesian approach for the rest of the lecture, and how the Bayesian approach works. The Bayesian approach works by assuming the beta follows a certain distribution, and this is required because in the prediction field, we always look at the dimensionality. The dimensionality for beta is called P, which I said is roughly 5 million to 7 million common SNPs in the European population. And the other dimension you would look at is the sample size, right? Even for depression, we'll probably have 1 million people. So you are facing a problem called, you have a higher dimension in the feature space than the sample size. You have more parameters to train than the samples you have. That is going to cause an overfitting. So what do? You can solve the problem by putting a restraint, which is a frequentist approach, a penalized term, or you can do that through a prior, which is to assume that the beta don't change freely. You can pick a single beta for every SNP. That's going to have a 5 million different beta that's going to overfit the model. Instead, you require all the beta to fit a certain distribution, and that distribution is going to regularize the beta so that you won't have that many parameters to fit. So the most naive approach, naive prior, is a normal prior. You require the beta fit a normal curve, a bell-shaped curve, right? So that basically assumes the betas are independent, all the SNPs are causal, which is an assumption from the infinitesimal model, and you assume they are normally distributed, and because we usually model the variance explained of the beta, the smaller the allele frequency you have, the larger the effect you have. That's one of the side effects of doing this modeling. So I want to pause here to make sure you're still with me. Any question you have in terms of the prior, why we need a prior, how a prior works? So I think this is the earliest, if not the first, paper using the normal prior to do the regularization in the PRS. It's called G-Gloop. And of course, there are other priors you can choose. For example, for some of the disorders we know it's not that polygenic. There is a central mass around effect size of 0. That means a large number of the SNPs have no contribution to the disorder. They have effect size of literally 0, and you want to reflect that. And how you do that? Sorry?
But this means that we have to know before what kind of model we estimate for the disorder?
Yes, you have to know. Well, if you know, you will be able to pick the best one, but usually you don't know. So what people does is they try a few of them and to see which one does better. So there is no one PRS approach that works for all the traits. For some of the highly polygenic traits, one method works better. For some of the less polygenic trait, the other method works better. So unfortunately, we don't know, but yes.
So like how it works, so we apply prior to each SNP, or we apply prior to like all the SNPs?
To all the SNPs.
To all the SNPs.
To all the SNPs, yes. Yeah. Yes.
Just a question. So how do you reconcile the difference between the standard GWAS approach where we're modeling each SNP independently, so you're not modeling the covariance between the SNPs?
Right.
At the same time, in your PRS approach, you're trying to put all the SNPs together.
Right.
So those are two different modeling functions.
Yeah, so for GWAS is a discovery. So you can you can treat each of the SNPs independently. All you want is a locus significantly associated with the trait of interest. So you don't really mind whether there are two SNPs correlated, both showing significance, or if you happen to miss one of them, it really doesn't matter because you're focusing on the locus. For the PRS, you're modeling the genome-wide profile, and you have to take into account of the SNPs that are the dependency structure of the SNPs, otherwise you're going to overcount them.
But wouldn't your effect size readers from the GWAS be wrong?
I'm sorry, what, I mean,
You don't account for the covariance between the SNPs.
yes.
Your effect sizes from GWAS are incorrect.
That's true. So if you have to, if I rephrase your question, if you have two SNPs in LD with each other, both of them are causal, the causal effect are going to bleed into each other and inflate it. That's definitely true. Yes, but in GWAS, people really don't, I mean, people care about the effect size, but not to the level of PRS. You have to more accurately model that. Yeah, so we always say PRS effect is a little bit off than, you know, the true effect. All right, so the point normal is just one example I was giving where you have a central, you know, mass in 0, means a lot of the SNP not being causal, showing no effect. The other extreme would be the, you know, what if you don't think your effect follows a normal distribution? You have some kind of a weird distribution, and that would be the infinite normal mixture, where you have a bunch of normal distribution added together, and because there are so many of them, you can use them to create any kind of a distribution. So, you know, this is just a bunch of different priors that you put on the beta. So I want to give approach my colleague Tian Ge developed a little bit highlight, because we're going to do the practice using this approach. It's called continuous shrinkage approach. It's different from the priors you have seen in that each of the beta here actually have their own distribution. If you recall, beta follows a normal distribution, and for all the priors you see, the normal distribution has the same. I mean, all the beta share the same distribution, but actually this beta has a different distribution for each of the variant. And how do we solve that problem? I mean, the whole point of doing the prior is to limit the ability, the number of free parameters we have to fit. How it solves the problem by giving each of the beta different distribution? Well, we have another regularization term on the distribution. So the beta, the variance of the normal curve, of the normal distribution for beta is being regularized by this phi j. J means different SNP, but phi j cannot change freely for each of the beta. It follows a gamma distribution. So that gives you a little bit more flexibility by doing a hierarchical model. You have, you know, different distribution for different beta, but all the distributions follow some kind of distribution. I hope I'm not confusing you too much. Anyway, so I think that's all you need to know about this approach. We'll revisit this when we do the cross-ancestry prediction a little bit. Next, evaluation of the PRS. You have the Bayesian approach, you re-estimate the beta. The next would be just simply use the new beta, and you use the genotype you have, do the summation, you know, which is very straightforward, and you will do that in the practice. I'm not going to go through that. But after the prediction, you probably want to take a look at how well I am making this prediction. And you can do that by using a simple linear regression if it's a quantitative trait. Just to make sure you include all the covariates in your prediction, because that would inflate your estimate if you don't include them. So basically, let's say if you have a height as your interest trait, you do a regression between the real height you measured in your target data set against the covariates, which is population structure characterized by the principal components, and your PRS. And you can compare the model with and without the covariate to see with and without the PRS to see how much PRS contributes to the model. So that is very straightforward. 2 linear regressions, you are done. What if you have a binary outcome? So that is getting trickier, right? Because, I mean, height is height. You can directly measure it. But for binary outcome, you are actually measuring the case control status, whether someone gets the disease or not. But really, the underlying quantity you should measure is the disease risk. You're comparing the PRS to the disease risk, not whether someone happen to have the disorder or not. So that is a little bit tricky. There are very naive one where people just treat the disease status as a quantitative value. You do the regression as if this is a linear regression. This is a naive and lazy way. Sometimes it doesn't give you a result that is too off, but we don't really recommend doing that. So the next approach is to treat the disease in a logistic regression model. Basically, you say, we know this is a case control study, and we do a logistic regression so that it captures the underlying, disease liability. But there is a problem, that is, what if you do a case control study and the case control frequency or the case control proportion really do not match your population prevalency of this disorder. Let's say if you do a schizophrenia study, you know the population prevalence for schizophrenia is roughly less than 1%, so which is the K here and this curve. And of course, you won't be only using 1% of the cases in your study. You don't have the power to find anything. You probably have 50% case, 50% control. Let's say it's the most common study design. So what would happen? This is the sample prevalence. If you have half of the sample as cases, this is what you would estimate as heritability, and you would probably get a heritability of 20-something%, while the true heritability is only 7%. And the reason is you are actually biasing the curve. So this is the distribution for your population, genetic risk. You can see that it's a perfect bell-shaped curve, which is expected. But if you have ascertained case control with 50% of the case, 50% of sample as case and 50% as control, you will have an enrichment of the higher risk part and less of, risk, less of the people in the controls are of less, genetic liability. So because of this weird shape, you have to do some adjustment to your R-square. So this is adjustment you should do. K here is the population prevalence of the disorder. Z here is the probability density function corresponding to the K. And this is simply, the population prevalence, and this is your proportion of case and control. Yes?
Does it make sense to, for erasing this enrichment, to go to the sample collection and, take, for example, people from families that we know have, one schizophrenic people from the family and taking the daughter or son of them as in the, they have the risk of being schizophrenic but are not yet detected.
Right.
So it's not high risk and it might lower the enrichment.
So the question was, does it make sense to ascertain family schizophrenia patient family?
Not the whole family, but people from the family.
And for what purpose if we do that?
Because in this enrichment situation,
Right.
because we take people that have schizophrenia as case.
Yes.
So we're obviously enriched.
I see. So you are saying you're using family members as the case rather than the. There are some studies showing that. I remember a couple years ago, people use not schizophrenia, but family member of people who diagnosed with disorder as case, and they did a GWAS, and there was actually certain power for that. So it's definitely something people have explored, and it worked, and. I agree. If you use that, it will probably look closer to the curve shown on the population distribution. But really, we already know how to fix this bias, so that's not a major concern here. And I think the using family member as a GWAS, as a proxy for the GWAS case, could be something interesting with the biobanks getting more and more popular. But that will be solve another problem. We don't have enough cases. We can use a family member as a case. All right. So I guess the really take-home message here is if you have two cohorts, if you're comparing two PRS prediction, you have to make sure you adjust for the case control prevalence. Otherwise, the predictions and the accuracies are not comparable with each other. And this is how you adjust for that. Any question on this? All right. If not, let's move on. So. Well, in addition to the R-square, and the other approach to take a look at how the PRS makes a prediction would be the comparing the odds ratio between the high-risk group versus low-risk group. This is how you do that. You separate the individuals into beings, and in this case, you create 10 quantiles, and you put 10% of individual in each of the 10 quantile, and you compare within each of the quantile how enriched your cases are, comparing with either the population or with the bottom quantile. I think in this case, it's with the bottom quantile. So comparing with the bottom quantile, the quantile with the lowest risk, the quantile with the highest risk has 20%, or 20 times of the enrichment as odds ratio. So that's the other way of looking at the, how accurate your PRS is in terms of the stratifying the patients. So the last thing in the prediction space is what matters in terms of the accuracy and power. So this is a very nice equation summarizing everything, and we can walk through the three most important factors. So first is the heritability. This is quite intuitive, right? If you have a higher heritability for your trait, the PRS would have better accuracy when they are used to predict the disease outcome. So that's why it's in the denominator where, the larger the H square is, the larger your R square is. The next factor is the effect number of SNPs, which is shown as the M here. If you have a larger M, that means if your heritability is spread across more SNPs, it's going to make your R square less accurate. And this is because each of the SNP will carry smaller effect, and you have random noise adding to that SNP because of the finite sample size. Of course, the accuracy will be lower. So the less polygenic, meaning the heritability is spread to less number of SNPs, the more accurate your PRS will be. So the M is in the denominator, and N is the GWAS discovery sample size. That's the sample size of the study you grab for your summary stat. And it's in the denominator of the denominator. So that means if you have a large N, you have a better power. The larger GWAS sample size you have, the better R square you're going to get. So three most important factors influencing the accuracy of your PRS. So this is a figure. It's basically reproducing what I told you, the complexity meaning more SNPs, simple meaning less SNPs, the heritability low and high. You can see, ideally, if you have a monogenic disorder, of course, you have 100% accuracy if it's a fully penetrant variant. And if you have low heritability and a very complex genetic architecture, probably don't bother trying at all. So it's probably very little chance to make a good prediction. But for most of the psychiatric disorders and autoimmune disorders, luckily we are pretty good powered with high heritability, even if we do face the challenge of the polygenicity here. And to complete the power discussion, I also want to say that the sample size of the target data set is also important, because that determines how well and how accurate you are able to calculate the R square. Let's say if you are only have 50 sample, 20 sample in your target, you probably won't have enough sample size to tell the case control difference. It's only 10 case, 10 control. You don't have the power to do that. But if you have 2,000 cases, 2,000 controls, things will be much easier. If there is a small difference between case and control, you will be able to capture that. So in practice, the sample size of the target data set is important, and also how similar your training and the target data is also important. Similar meaning the phenotype definition as well as the genetic ancestry. And I'm going to step into the genetic ancestry in the next slide, but before that, any question on the power and accuracy of PRS? Yes? I'm going to touch that in the ancestry part. So would that do? Yeah, I can go, because that is a little bit relevant to how we model the cross ancestry thing, and we can discuss into more details. All right. If not, PRS across ancestries. So this is a paper Max led in 2019. We were able to put together a quite large schizophrenia cohort from the East Asian ancestry, and we noticed something quite interesting. That is, the East Asian cohort, as you see here, is only half or less than half of the European cohort here, right? But when you use the East Asian and European to predict the risk in East Asian independently, you will see that even if the East Asian sample size is still smaller, it actually predicts more accurately than the European cohort, with only half of the samples here shown here. So around the same time, my colleague Alicia Martin also published this quite helpful paper that shows there is underrepresentation, a very clear underrepresentation of the European of the non-European samples in basically all the genetic studies, and the ability for the PRS to make prediction outside of its own discovery ancestry is pretty bad. If you have a relatively close ancestry, you probably get half of the accuracy. If the genetic distance is too far away, you get basically 20% of the accuracy. So that means we really have to think of ways to improve the cross-ancestry prediction. And one way my colleague and I have been thinking is, rather than making the competition, using one, or forcing you to pick one of the two ancestries, is it possible we create a method that combines both ancestries to make the prediction? And can this method works better? So this is how we do this, and this is just a recap of what has been done in the field before we started. People have the single ancestry method. You have the GWAS summary stat. You make the prediction. You do the PRS calculation, which is what you have heard in the earlier part of the discussion. And there's a meta-analysis approach, which is you can do meta-analysis combining both populations, right? And you can treat this meta-analyzed GWAS as if it's from a single ancestry. But there are problems, which LD reference you use, and people would probably do LD on both and combine them. So and what if the population have different genetic effect? It won't be modeled in this. So this is a quite naive way of doing that, but people have been using that before a more sophisticated method became available. And the other one would be to do the prediction for each of the two ancestries separately and do a linear combination to create the best linear combination of the score from both ancestries. So these are the work before us. But this approach has a problem in that the two ancestry won't reinforce each other. You won't be able to leverage the similarity between the populations. You're only able to do the combination post hoc. So we had the idea that what if we do at the very early stage, combining multiple ancestries, we use the estimate from one ancestry to reinforce the estimate from the other, and we can leverage the LD in a more principled approach. So this is how we do this. We take all the ancestries into the approach, into our method, and we give you estimate for each of the ancestries separately, because we don't know whether you're going to use the weight to make which ancestry you're going to make the prediction in. So we're going to give you the ancestry specific weight, combining all the summary stats from all the ancestries. And then you can use that to create the linear combination that maximizes your prediction accuracy. So this is, I'm going to get to the mathematics a little bit, how this works. But before that, any people with questions? Maybe after the math, we can discuss more about that. So this was built on the PRS-CSx, the continuous shrinkage approach. Just to refresh everyone's memory, this is the equation you have seen numerous times in this slide, which is simply a summation of your genotype times the effect. The effect is not from the GWAS, but from the regularized, Bayesian approach that's being adjusted for the causality, LD, and for the GWAS effect. And the way we estimate the beta is we ask the beta to follow a normal distribution with a mean of 0 and a standard deviation defined in this way. And the continuous shrinkage differ from other prior in that we allow beta to take a different standard deviation term for each of the beta. And we regularize the distribution of the standard deviation by this gamma distribution. Any question? All right. So here's the trick we do. So what if we want to extend this to multiple ancestries? Well, we have to allow each of the beta to differ in different ancestries, right? We can't assume the betas are the same, but that would kind of lose the fun if you assume the beta can freely change across ancestries. What's the point of combining them together? So if you think really hard, and if you actually go back to the paper in the 2019 Max Lam paper, you will find that in most of the scenarios, the betas are quite consistent between ancestries. There are heterogeneity across ancestry for sure, but the betas are in general consistent. So we have the idea that what if we force the distribution of beta to be the same across ancestries. We allow the beta to differ, but we force the distribution of the beta to be the same across ancestry using the distribution to combine the beta. So that is what we do. The K here means ancestry. You can see we have the phenotype to be specific to the ancestry, genotype of course, beta of course to be different across ancestries. And this beta is conditioned on K, also on the ancestry. But what is not ancestry dependent is this distribution. So basically we ask all the effect size distribution. The distribution in different ancestries follows the same term. That's the only underlying assumption. And in this way, we can reduce the complexity of the beta, the freedom of the beta, and we can force them to have some similarity across ancestries. Any question on this? Yes?
In the previous slides, you talk about the linkage disequilibrium.
Yes.
I don't understand how this is integrated in the model.
Yes. So the linkage disequilibrium, that's a very good question. The linkage disequilibrium will be modeled in this beta prior. When we consider the beta prior, we consider the linkage disequilibrium. So that will be automatically adjusted in this.
So like you have like one variance linked to variance in other part.
Yes.
You have the same beta.
Yes.
One alone have lower beta.
Yes, so that once you consider the LD, one of them will have a higher effect, the others will have lower. I think what might happen is the effect will be spread across all the variants rather than giving all the way to one of the variant. I think that's what's actually happening.
Okay.
Yeah.
So the software is considering also the LD reference panel. Let's say if we are doing analysis for European ancestry, so we are considering the panel for Europeans. So there's like a term like Gibbs sampling. So how like this information is like the Gibbs sample is using? Is it using through the reference panel or?
Yeah, so when you do when you try to estimate the beta, if I go back here, when you try to estimate the beta, we estimate the beta for each of the population separately. It's precisely because of that reason. We want to use that population-specific reference panel to do the beta estimate. And when we do the beta estimate, there is a Gibbs sampling to estimate the beta for given the prior and the genotypes you have observed. All right. Oh, there we go.
Would it make sense to use PRS-CSx
We gave it a try. It didn't work very well, so we're still working on that. That's something I think is still quite unsolved in the PRS space. We tried some very naive idea, which is for the mixed individual, we can separate the ancestral tracks for the individual. And if you have an African track, we use African weight. If you have a European track, we use European weight. But it didn't work out very well, probably because of the ability to assign the ancestral tracks, or I don't know. But I don't think that's being fully solved yet. All right, I'll probably keep moving considering the time. And so this is a performance we have evaluated using the PRS-CS. So first, I think the first message I want to tell everyone is if you already have a large European cohort and a relatively smaller Asian, African cohort, it probably won't help you much for your European prediction by adding the smaller non-European cohort, because the heterogeneity will probably kill all the power you bring the additional data to the data set. So that's what we learned here. This is a prediction using only the European data. This is a prediction using European plus African sample, and you really don't see they differ that much. So we honestly admit we probably won't be able to help European that much. However, if you look at the other ancestry, the African ancestry, this is what if you make the prediction using the African discovery set, what if you only using the European, and what if you use both. You will see there's an overall improvement even if you use a naive PRS approach. And when you use the PRS-CS approach, it actually gives you the best improvement. So this is from simulation, and what if for real data set, again, in the European prediction, this is the performance you get for the European, and this is the performance you get from all the ancestries, which really we are not helping much by adding the Biobank Japan to the European data set. But in the East Asian ancestry, you will see there's an increase in performance compared with using any of the single ancestry, and even in the African ancestry. See here, we have the white British from the European, the Biobank Japan, the Asian ancestry. There's no African ancestry individual added, but still we're able to see a much better performance, likely because the added Asian ancestry captured to some degree the African, unique genome variants. That's our hypothesis. But still, you will see that for African ancestry, we have some improved performance. So this is for schizophrenia study, the same schizophrenia prediction in the East Asian ancestry you have seen. This is for the East Asian, predict East Asian, European predict East Asian, a little bit worse than the East Asian predict East Asian, and this is by using all the ancestries. You will definitely see a much better improvement in the accuracy. And this is a figure showing the, the quantiles comparing the top quantile with the bottom quantile. This is using the PRS-CSx, and this is using the other approach. You get much better, enrichment of the cases once you have the multi-ancestry properly modeled. So in summary, I showed you how to do the PRS calculation, how to evaluate its performance, and discuss some of the concerns and approaches to transfer the PRS across the ancestries. So Alice will take over after me to, do a demo, and hopefully you will be able to use the server to follow her to actually do the exercise. But before Alice take over, any question? Yes. Sorry.
So if you have an African ancestry target data set, would it make sense to use like 3 discovery GWAS, like European, Asian, and African, or would it be best to just use European and African discovery?
We find adding the East Asian always helps a little bit, yes. Okay. You should use as many as GWAS summary stats as possible, assuming these are reasonably powered. If you have 100 case, 100 control, probably don't bother. But if it's a reasonably powered, it's always good to add them. Yes?
What is the ballpark proportion of the new ancestry sample that we need to add to improve the power?
It depends on the genetic architecture of the disorder. For schizophrenia, I feel a more decent 3,000 case, 3,000 control is probably needed. But if you have autoimmune, that's 500 case will probably make a difference. Yes?
So the number of markers that go into these models are restricted by the LD panel?
Yes, exactly.
And the LD panel usually is only on the HapMap marker.
Yes.
Predominantly European ancestry, and the error frequencies don't match with their other ancestries.
Yes.
So if you can scale up and use the
So,
LD panel and
yeah, I think we have released the 1,000 genome one, right? I think the PRS-CSx probably have released the 1,000 genome.
markers are still the HapMap.
So, okay, so I can talk to Tian. I agree. The HapMap is array-based, so it's definitely biased towards European. Moving to 1,000 genome is probably makes sense. Yeah, you're right.
So I have used CS tool by considering European ADHD GWAS in East Asian samples.
Yes.
East Asian reference panel, and I've calculated the polygenic risk scores in East Asian. You think it's a valid analysis by considering European ADHD GWAS and East Asian reference panel?
The reference panel, I think it has to it has to match the discovery GWAS. So if you are using the European GWAS, you have to use the European reference panel, because
and then I can calculate an East Asian sample.
You can calculate the East Asian sample because that's a part of the LD comes into play, right? Your GWAS is being complicated by the LD. The SNPs are correlated by the European LD, and you need the European LD to sort of deconvolute that effect.
Okay. So because we don't have any large scale ADHD GWAS for East Asian, right?
Right.
So for the time being, if I want to do the analysis, you think it's a valid analysis using the CS2?
It is, but you have to use the European reference panel. That's the only thing you need to change.
So I was just thinking maybe at a later point when I will write it, so maybe the reviewers will ask why is it a valid thing to do with European GWAS?
I mean, getting response to review is another story. I think that's the right thing to do. But to satisfy your reviewer, you probably want to try a few different approach. For example, it's a naive approach.
Do you have any other solution for that? You don't have
Exactly. If it is something you don't have a perfect solution for, and the reviewer has doubt regarding your approach, you probably want to try a few, like the naive approach, or maybe try do the reference panel in both ancestries and show the reviewer really it doesn't matter. So, I mean, you're really not defending, well, to some extent, you're not defending approach, you're defending your conclusion, right? If you want to show the reviewer there isn't a perfect solution, I tried, reasonable solutions and they all come to the same conclusion, the conclusion is reliable and robust, that generally do. Yeah.
Okay. Yeah, because in this CSx paper, you have like compared different approaches in European by considering like African and GWAS and like this kind, and
Yep.
compared like different approaches. So it was like working, but CSx was like working well as compared to others.
Yeah, exactly. Yes.
So do you have methods within the PRS-CSx to check for the QC, some of the things that you have mentioned today, like the sample overlap, the choice of things and target?
No, we don't. Unfortunately, we don't.
So
Yes.
it could be a cool idea to automate these things so that people who don't know
Yeah.
the best things can just use the methods and that can make it simpler.
Yeah, I think Raymond is here, right? We're writing a grant to do that, to create a pipeline, so the PGC, investigators will be more easily to run things, putting everything together, like you said, and people can run things more smoothly. That's something definitely on our list to do. Yes.
A simple modeling question. So at the end of the day, you're training a PRS model and applying it to an external holdout sample.
Yeah.
How well it does. But what about incorporating cross-validation within the training data itself while you're training your model? Do you think that would lead to a more robust PRS model?
Yeah, so if I recall correctly, the cross-validation always have a little bit inflation. So, I mean, if you have no other way, I mean, if you don't have a validation and a testing, definitely you can do the cross-validation.
You still have the validation piece.
Right.
You still apply it, but during the model training itself,
Okay.
doing the training and developing the training model using cross-validation.
But you won't be able to have the individual data access for the discovery GWAS. Are you saying the GWAS part, you redo the GWAS with cross-validation? It's mostly the data access. You don't have access to that. Yeah, like 1 million sample MDD, the depression GWAS, you will only get the summary stat. No one will do the cross-validation on the PGC for you. But we somehow, we to some flavor do that. I don't know, for recent PGC paper, for the earlier ones, we do the leave-out prediction. That means if you have 20 cohort contributing to the GWAS, PGC GWAS, you do the discovery using 19 of them, and you estimate the risk for the one that's being left out, and you do that, across all the 20 cohorts. So that's something people did, at least in the past. All right. So we have 6 minutes. So
we've got a break scheduled at 11 o'clock, which is
Okay.
in 5 minutes' time.
yes.
So we can be flexible about that, but I just wanted to make sure
Right.
before we started on Alice's session.
Yeah.
Do you want to take the break now? And
I think
then
we'll take a
on,
break,
or do you want to
but,
get started and then?
But before the break, because we're going to use the Jupyter notebook, it takes like 5 minutes for the server to launch the notebook for everyone. So so Alice will do a very quick demo, definitely within 5 minutes, to show you how to launch your Jupyter notebook. All you need to do is to make sure it's in the queue waiting to be started. It took 5 minutes for my job to be, running since I put it in the queue. So probably we do that before we take the break. All right.
So if you could start with logging in to the server, that will be perfect. And after you logged in, whether through Doornode or the Snellius, both are fine, supposedly. You could create a working directory, either under your root directory or the project space. Either will work, as long as you remember that directory. So there is a text file that shows you how to launch the Jupyter Hub. Basically, if you go to this directory, you will find this text file. And if you open it by less, L-E-S-S, space, and then the file name, you will be able to see it, and then you could copy paste it to the terminal, and it should run like a bunch of code, and the explanations are in the file as well. Are there any questions or? Yes. Yes, this is the only part that you have to put in like by hand. The other part you could copy paste. Of course. Is anybody successfully running the command through the file, copy and pasting? Oh, great. So basically what we are doing here is load several modules to launch the hub, and then create a virtual environment to work with, and then install a few packages, as we'll use them in the tutorial. And I'm here to answer any tech questions. So for people who could open the Jupyter Hub, that's great. I was not able to do that. So I'm just gonna run through the overflow of the planned workshop and then see how could we adjust to that because of the difficulty on the server. So we were supposedly to first run the PRS-CSx using the terminal.
Sorry,
yeah, of course.
Can I just check? Can people read this size on the screen? Or,
it's pretty small.
I wonder if it's my failing aging eyesight.
Thank you for that.
And I'm not proud to admit this.
Okay, should be better right now? Awesome.
Great, thank you.
Yeah, thank you. So the first step is to run the PRS-CSx. And the second step, we'll get some matrices out of it, files out of it that we want to convert them to matrices for computation. And then as Hailiang just mentioned in the lecture, we want to run a regression to find the weight parameters, how to attribute, like which proportion to attribute to which population. Based on this equation, this is the key equation we want to work on for the workshop today. The Y is the phenotype. In this workshop, we use simulated phenotype. So it's not attached to any actual height, meaning or schizophrenia disease diagnosis. It's just simulated for a vanilla demo. And the A hat is something we want to calculate, the weight to put on one population's genotype matrix. And this multiplication, if you remember from high school knowledge, two vectors timed together get us a scalar, and we want to time this scalar to get a matrix on phenotypes. And this one is true for just the European population. And X here is a genotype matrix. Do we have a marker by any chance?
A marker?
To write on the board? Yeah, because I'm a visual learner, but it's okay if we don't have any. All I want to tell you is X is the genotype matrix. The rows are each person, and the columns are the variants, and the entries are the allele count of each variant. So it's either 0, 1, or 2, so we can put them into calculation, if that makes sense. And the weight matrix is just a single column matrix. Each row is each person. So for example, X has the dimension of n times m, then W would have the dimension of m times 1. So together, we have a single column of phenotypes that give us the Y to calculate. Sorry, we don't have a mark. It would be much easier to explain with that. But I'm here for questions if you want to dig into that. So this is the equation we base on. And then after getting the A hat and B hat, we want to predict the phenotype on both the validation and the test data set. Of course, test is the target. And then we will also plot the true values against some predictive values to just get practice in plotting. And then finally, we'll evaluate the model using deviance-based R-squared. Any questions regarding the overall flow?
What steps, at what step do we have like PRS?
Oh, it's just the first step.
Okay.
Yes.
Can you explain the matrix dimensions again? It is
The matrix,
the dimensions of the matrix.
the dimensions of matrix? Yes. X is person, like the number of individuals times the number of variants. And WES and EUR are the number of individuals times 1. Just the phenotype. So the weight of each SNP. Sorry, the...
So it's the number of SNPs.
Yes.
And the weight.
Misspoken, yes.
That makes
Yeah, okay, great. Because I was not able to run PRS-CSx on the server, I'll just use the GitHub website. GitHub. To explain how to do that, so to get it prepared, we will have a few things, including the whole package, the reference panel, and the SNP information downloaded, and that's already in the server. And then to run it, it's just pretty simple. There's just one line of code that you put into the command line. And the reference directory, including the reference directory, the bin file, and the summary statistics, the population and number of GWAS sample size, and a bunch of directory informations. The details you could find on this GitHub page, so I will not expand on that here.
So like number of GWAS is cases plus controls, right?
Let's take a look. So for number of GWAS, that might be a
Just cases
professor
or
question.
cases plus control.
Professor, do you have any answers to that?
For quantitative trait, it's just your sample size. For case control, it should be your effective sample size. That's divided by 1 over your case, 1 over the sample size of your case, plus 1 over the sample size of your control. And I wish
Continuous trait is just like
continuous trait is there's no case control, right? It's just like height is all the samples that goes to your GWAS, right? For case control, it's the effective sample size. Which I'll probably type it in the Slack channel so people have the.
Okay. Any other questions regarding the input? So if not, this should give us 2 output files that contains a bunch of ID information, variance information, and most importantly, the weight for each SNP, which is the effect size. And now we have the output. So this one runs on my computer locally, but if you have it open on the server, the instructions should be pretty clear, and the change of directories are labeled, like change your directory, something like that. Can I have a show of hands? How many people can access the server-linked notebook? Oh, quite a few. Awesome. Great.
Can you share this code by email?
This.
Can you like get this code by email?
You mean the?
Share this link.
It's on the Slack.
It's on the Slack.
Yes, I will share everything like after this. But for now, if I only share the script, you will still not able to run it because the reference panels are on the server. And it's.
We just want to have a look at the code.
Oh, okay, awesome. I'll share it right now to the SOC. Yes. And there are two versions. One has some things ripped out, so you can, like, the intention is you can copy paste and learn line by line. But the lecture version has all the actual code in them. So your preference.
Sorry, I'm a little lost because it's me right here.
No.
So I was able to log into Jupyter.
Yes.
And which part are we supposed to now put in the terminal?
Oh, we are not using the terminal right now, so we are using, we copy paste the both the worksheet version and the lecture version to your working directory earlier. So now you can just double click to open them. Yeah, they should be already in your working directory. And firstly, we did some matrix preparation because this file, can you everybody see? Okay, probably better. This file should be the PRS-CSx output, and we are truncating only the variant information and the weight information to another file so we can use them directly later. So that's what we are doing here using the command line. And then we read in the files and then put them in the directories by this built-in function of pandas package. And the zip function just pairs the entry 0, which are the variants, to the corresponding weights. We need to do this step because we want to find the overlapping variants between two populations, East Asian and European, which are the examples we are using here. And then by a couple of innate functions in the Python package, we could finally output a list of combined variants, overlapping variants between those two populations. For later use, we want to write it out as a file as well, so it's stored both in a NumPy array, which is just a data type to store it, and also an output file. Any questions so far? So I know people are running into some tech issues opening the file and everything, and our adjusted plan right now is just to focus on the demo. I'll explain it line by line, the chunk of codes, what it's mainly doing. And then after maybe 10 minutes of demo, we'll focus on how to actually implement it in your computer and server. Does that sound good? Okay. Awesome. So for, if I can have the attention, that would be great. So after preparing the genotype matrix, we want to prepare the weight matrices as well. And that is actually a lot simpler than what we did above. It's just taking the variance and convert it to a NumPy array, which is a mutable data type that we can use for later analysis. That's all the weight matrices. And the next step is prepare the genotype and phenotype matrix, as we saw in the equation X and Y, and then split them into test and validation data set for training and testing purposes. In this step, we can take a look at the data we got initially. I manipulated a little bit, so it could be put in one file. As I said before, the rows are the number of individuals, and the columns are the variance. And the last column, I attached the phenotype to it as well, but we will separate it later for two matrices. And these are the dimensions of the matrices if you want to take a further look. After we separate the genotype and phenotype, we want to split both into validation and test. I was trying to do it using an innate function, but it didn't work out as well because of the number, I think, round up thing. So I just did it manually, set up a random seed for the purpose of replication. And then in this workshop, we just set the validation proportion to be 0.4. So 40% of the data set would be used for training purposes, and the other 60% would be used for testing purposes. And then calculate the actual number using the data set you have. And this step is just setting some random indices to be put into as validation, and then put the rest into the test indices so they could separate easier using those indices. So each line, we make sure that each variant is still corresponding to the correct weights. And after all the preparation is done, we can do regression to find the weight parameters to put into. Again, we need to prepare the model input by multiplying the two scalars, the two matrices, and then we can fit them into the model, which is an innate function of the scikit-learn package. And you can use many other ways to implement it. This is one of the most, I think, user-friendly way. We set the intercept to be false because in the equation, you might notice we don't have any intercept as well. The more statistical reasoning, you can ask Professor Hailiang Huang for that. But to my understanding, the reason for that is because we're calculating the relative risk instead of the absolute risk, and the intercept is not a common practice to put in the training. And after feeding into the model, we will hopefully get our A hat and B hat as the model coefficient. Is basically running a regression and get the coefficient out of it. So in this case, the way I interpret it, A hat and B hat is around 84% of the data will come from the East Asian population, and around 13% would come from the European population, and that gives us the best predictive power or result. And this number could vary if you somehow scale the equations and scale the matrices to some other parameters. So as long as the proportion is reasonable, it should be fine. And also just a note, we're using simulated phenotypes, so you might see very different things in real data sets. And after getting the weight parameters, the next step would be predict phenotype, mainly on the test data set, but also we do it here on the validation data set to just get a sense of it when drawing the graph. The way we do it is do a regression as well and putting in the A hat we just got. And that is the same thing here for the test data set. And step 5 is plotting. We want to see how it looks like for our true values to be against our predicted values. And a graph we could see hopefully looks like this. The true values are against the predicted values, and this is the line when they are in perfect correlation, and this is the trend of the data. Of course, in real life, it might not be that beautiful. And the last step is to evaluate using a parameter called the deviance based R-squared. So basically what this is a residual deviance. It's the total squared difference between the true output values and the predicted values. We have some functions for calculating it, but the equation is also pretty straightforward. And the deviance we can see here for the predicted data set is this. And then to evaluate it further, we want to calculate it. We want to compare this prediction with a null deviance, which means the null deviance, the null model predicts every instance based on only the mean of the output variables. It's basically not doing actual work. And we want to compare this to the null to see how our methods could be evaluated and how there could be an improvement. And after dividing those and then minus those, this result, we could get the R squared, which is around 0.5% or 0.49-ish, which is looks really good because we're using simulated phenotype. That means, basically, to my understanding, 50% of the correlation could be explained by PRS. Yeah, and that's basically the overview of it. I know technical questions where difficulties is there, so I'm gonna walk around and help with you guys to go over this tutorial. And for statistical reasoning or higher level questions, please ask Hailiang. And for more like Python grammar questions, I'm here for you. Yes.